All right, hello out there. Welcome to my channel. This channel does educational content, and we tend to look at theories of everything, and take deep dives into them, probe into how you can use them and what you can use them for, especially helping you with your paradigm shift and your adaptation to 5D consciousness, your holistic worldview, and things like that. Today is our 450th video that we've done on the reciprocal system of theory from Dewey B. Larson. The reciprocal system is pretty obscure at this point, but I'm convinced that somewhere in the future it will be the standard for all of our academic pursuits, because it is a system that you can plug into any subject and arrive at logical and correct answers for any question. You just have to learn how to use and manipulate the system, and then figure out how it connects with the subject matter that you're interested in. The reciprocal system was first originated by Dewey B. Larson back in the 20th century. In 1959, he proposed his two fundamental postulates about how he believed the universe operated. And then he went through a process of deduction, of taking those postulates through an if this then that type of approach to arrive at a theoretical universe. How the universe would look if my postulates were correct. And then in books like the one we're looking at today, called Basic Properties of Matter, he compares his theoretical findings with the empirical findings of the legacy scientists that they have arrived at through their laboratory experiments and compiled in their tables. We're looking now at chapter 6, which is called Specific Heat Patterns. So he goes over some of the specific heat is basically the amount of heat that you have to add to a substance in order to raise the temperature of that substance by a specific increment. And he went through, in yesterday's episode, at the beginning of the chapter, he went through some of the various considerations that he took in figuring out how to choose a probability limit, because you need to use probability in general, because you don't do your laboratory experiments on single atoms. If you were using single atoms, then you could use a line segmented curve, a curve that had line segments that inflected at various transition points of the atom. But when you are doing these experiments, you're using billions or trillions or whatever of atoms. And so they conform to an average. And so that is where he's trying to figure out this probability unit. But before we get into that, we're going to just look at the two fundamental postulates a little bit. The two fundamental postulates basically boil down to 7 assumptions about how the universe operates. And the reciprocal system is also known as the universe of motion, because Larson was not the first, but was, I guess, one of the few people who tried to build their universe upon motion. Not matter, or not energy, or force, but motion. The universe, his first postulate, or his first assumption, part of his first postulate, is that the universe is composed entirely of one component, motion. Now, when Larson says that, he is referring to what he calls a scalar motion. This is a motion that has a magnitude, but it has no specific direction. This is a motion that's recognized by science, but is kind of ignored and has not, science has not discovered its general applicability. It's seen as being kind of a backwater. You can describe, or you can envision a scalar motion by taking a balloon and putting some dots on it with a magic marker. If you blow up the balloon, all the dots will be moving away from each other. Every dot will be moving away from every other dot. And even the locations between the dots are moving away from each other. So every point on that balloon will be moving in every direction. There is no specific direction. They're all moving in every direction. And if you suck in the balloon, then they will be moving toward each other in the same manner. Larson refers to these motions as the progression and gravitation. The outward motion is called the progression. The inward motion is gravitation. And those are scalar motions, motions that have a magnitude but have no specific direction. And that is the source of his universe of motion. Those are the most basic primary kinds of motion in his universe of motion. You also have to remember that this is a universe of motion. So you have to be able to accept the concept of motion without anything moving. Motion precedes the thing that is moving. And motion, in fact, is the thing that's moving. That is the other kind of aspect that comes into play here, is that the second one of Larson's assumptions, or I don't know if it's the second, but it's part of his first postulate, is that the motion comes in two reciprocal aspects, space and time. So where he gets the name the reciprocal system. Motion is the relationship between space and time. Space and time are reciprocals of one another. They do not exist in and of themselves. They only exist together in motion. And motion is basically a fraction, with time or space as the numerator and space or time as the denominator. And you can see that in speed. The bike is going 10 miles per hour, 10 miles of space in 1 hour of time. Space over time is speed. That is a relationship between space and time. And you can see that it is a reciprocal relationship. If you decide to double the speed, you can say the bike is now moving 20 miles per hour. Or equivalently, you can say the bike is now moving 10 miles per half hour. You can either multiply the space or you can divide the time. That shows a reciprocal relationship between space and time in motion. And this is another conceptual hurdle that you have to get over to get to, with the universe of motion, is that motion, space and time are generally seen to be the background of our universe, that we are existing in this three-dimensional spatial continuum that's still, that we move through, and that time is marching on and on and on and progressing. So what we're really seeing is 3 dimensions of vectorial space, or what Larson calls coordinate space, not scalar. These are, vectorial dimensions, directions, and a scalar time. Time is still progressing forward, always getting later and later and later, but in no specific direction. And this is kind of how we see the background. We see space and time as a container of the universe. But in Larson's system, space and time is not the container. Space and time are the contents of the universe. The universe is made out of space-time or motion. And so, again, you have to be able to conceive of motion without anything moving. the thing that's moving is also motion. So we have to kind of be able to get with those ideas before we can even approach the reciprocal system. Okay, another one of Larson's assumptions is that motion is the relationship between space and time. Motion comes in 3 dimensions. Space, time, and motion all come in 3 dimensions. Now, you can have your 3 dimensions of space, like your XYZ coordinates of your coordinate space, or what Larson calls the spatial reference system. And this really comes about by the assigning a reference point to your scalar progression of the dots. If you arbitrarily decide that one of the dots is motionless, you pick one of the dots and say, this one is motionless. Well, then you can start to impute directions to the other dots. And in fact, it looks like there's a force field involved that is either causing repulsion in the case of outward motion or attraction in the case of inward motion from all the other dots to your reference dot. But you have to recognize that this is not a force or a force field, and that these motion or directions, and these motions and these directions are related to your reference point, not to the motion itself. The motion itself has no direction, and there is no force. Every dot is pursuing its own course. Every dot is moving inward or outward in all directions. There is no force. There is no connection between the dots. They are all moving on their own volition. And so, but that, if you do abstract the system like that by assigning a reference point, that's where you get your vectorial motions of your spatial reference system, your 3 dimensions of space, your coordinate space, to go along with your scalar time, your clock time. And as space and time are reciprocals of each other, it follows that this same thing would hold true in a different environment of the universe, where you would have 3 dimensions of time in a coordinate manner, in a spatial still frame. And you would have space as the scalar motion. Everything is getting farther and farther and farther apart, just like on the surface of an expanding balloon. So there you have what Larson calls the temporal reference system, and you would have coordinate time and clock space. And what's important to recognize is those 3 dimensions of space in the spatial reference system and the 3 dimensions of time in the temporal reference system, both of them can be described by a single dimension of motion. So you have, in the universe of motion, you have 3 dimensions. So there are 3 scalar dimensions of scalar motion, but they cannot be described by a reference system. You need a whole reference system just to describe one of those dimensions. So there are 2 other dimensions that cannot be described by a reference system. So that's the limitation of our reference systems, and it's something that we just have to live with. Okay, then the 4th assumption of the first postulate is that space, time, and motion come only in discrete units. You have to have a full unit of space or time or motion in order to have that entity. If you don't have a full unit, then you don't have it. And the units are small. The unit of space is 2 millionths of an inch. So that's microscopic, but very large compared to the size of atoms. And the unit of time is 1.52 times 10 to the minus 16 seconds. So less than 1/6 quadrillionth of a second. And unit speed, speed, remember, being space over time, unit speed is 1 unit of space in 1 unit of time. Larson calls that unit speed, and that works out to be the speed of light. So this speed of light is the speed of the progression. The progression progresses 1 unit of space in 1 unit of time, the speed of light. So that is what Larson refers to as the null point or the neutral point. The 0 point of the universe of motion is outward motion at the speed of light in all directions. Larson refers to that as the progression of the natural reference system. And this is the midpoint of the universe of motion. He uses that as a reference point, the natural reference system. And it's a moving reference system, but it is the reference system to which nature actually conforms. These spatial reference systems and temporal reference systems are artificial constructs of assigning reference points. So if you have this progression of the natural reference system as the midpoint, you have half the universe moving faster than the speed of light, which is blasphemy to the legacy scientists, and then half the universe moving slower than the speed of light, which is what the scientists recognize. Larson refers to these respectively as the cosmic sector and the material sector. In the material sector, we have the spatial reference system, coordinate space and clock time. In the cosmic sector, we have the temporal reference system, coordinate time and clock space. And so as you cross that boundary, that unit speed boundary, the rules invert, and the roles of space and time are interchanged. Now, within both the material sector and the cosmic sector, there is a subregion. So 2 subregions that Larson refers to as the time region in the material sector and the space region in the cosmic sector. The time region in the material sector is the result of the discrete unit postulate. If you don't have a full unit of space, then you only have time because the universe is made out of space-time. So it has to be one or the other or both. And if you don't have a full unit of space, such as an atomic interaction that is occurring in less than 1 unit of space, or where 2 particles or atoms approach each other to 1 unit of space, then they can't get any closer than that. The only way they can get closer than that is by going into the time region and reversing the time-space relations. And so now they, instead of moving further in space, which is impossible because they are already at the boundary of 1 unit of space, they move outward in time, which is the equivalent of moving inward in space. Larson refers to this as equivalent space. So the activity is really occurring in time, but we see it in space because we only see space. We don't see time in our vantage point of being anchored to the spatial reference system. But when we do look into this other boundary, across this other boundary, whenever we look across a boundary, what we see is reduced by what he calls the interregional ratio. This is kind of like what's lost in the translation when you look into a different region. And we see equivalent space as a second power entity. Anything that we see in the time region, we see it as a second power entity because space equals 1 over t, and speed is space over time. So in the time region, speed would equal 1 over t squared. So that's like a second power entity. Now, atoms and particles come about by basically taking that progression of the natural reference system and reversing it. And so this outward motion has to be reversed to that inward motion of gravitation. And there are several motions that are required to do that. The first is the photon, which is a vibratory motion that is kind of basically stops the progression in one dimension. Again, there's 3 dimensions of motion. So in one dimension, the progression is stopped, but it still moves outward at the speed of light because of the motion in the other 2 dimensions. And then that photon needs to be rotated 2 more times in order to achieve gravitation and to become an atom. And so these are things, and so Larson's periodic table, his elements all include a 3-number sequence, 2 two-dimensional rotations and 1 one-dimensional rotation in the opposite direction. The 2 two-dimensional rotations alternate, and the third rotational motion is optional. In the inert gases or the noble gases, it's 0, and it can be positive or negative. Okay, let's take that information and apply it to some of Larson's work here in this Basic Properties of Matter, Chapter 6, Specific Heat Patterns. I'll try to, there's a bunch of terms here that you might not understand. Don't try to understand the whole thing. Just try to glean kind of the big picture and like what he's trying to get at. You know, he's really just trying to get at that we can determine the properties of these various atoms, the basic properties, through deduction from those basic assumptions. That first postulate. The second postulate is really just axiomatic. The universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. Okay, whether all of the curves in the same maximum deviation, point 2, are coincident below t sub 0, the first transition point, is likewise, or really the origin, the temperature origin, is likewise still uncertain. There is a greater spread in the observed specific heats below point 2 that then can be ascribed to errors in measurement, but most of the scatter can probably be explained as the result of lack of thermal equilibrium. At these low temperatures, it no doubt takes a long time to establish equilibrium, and even an accurate measurement will not produce the correct result unless the aggregate is in thermal equilibrium. It is significant that the specific heats of the common elements which have been studied most extensively deviate only slightly from a smooth curve in this low temperature region. Figure 6 which shows the measured values of the specific heats of 6 of these elements on a temperature scale relative to T sub 0, demonstrates this coincidence. So Larson is basically saying that he's having a lot of trouble comparing his theoretical results to the data from the scientists because their data is not terribly accurate in this case, and that there are some limitations to their being able to make accurate measurements of the thermal specific heat at very, very low temperatures, where it's hard to, you have to be able to establish an equilibrium before you can start making these measurements. I believe that's what he's saying here. If the probability unit is the same for all or most of the elements, as these data suggest, the deviation of the experimental curve from the theoretical curve for the single atom at the first transition point, T sub 1, should also have a constant value. Preliminary examination of the curves of the elements that follow the regular pattern indicates that the values of this deviation actually do lie within a range extending from about 0.55 to about 0.70. Considerable additional work will be required before these curves can be defined accurately enough to determine whether there is complete coincidence. But present indications are that the deviation at t sub 1 is, in fact, a constant for all of the regular elements and is in the neighborhood of 3 times the deviation at t sub 0. With the benefit of the foregoing information as to the general nature of the deviations from the theoretical curves of Chapter 5, due to the manner in which the measurements are made, we are now prepared to examine the correlation between the theoretical curves and the measured specific heats. In order to arrive at a complete definition of the specific heat of a substance, it is not only necessary to establish the shapes of the specific heat curves, the objective at which most of the foregoing discussion is aimed, but also to define the temperature scale of each curve. Although the theoretical conclusions with respect to these two theoretical aspects of the specific heat situation, like all other conclusions in this work, are derived by developing the consequences of the fundamental postulates of the reciprocal system of theory, they are necessarily reached by 2 different lines of theoretical development. For this reason, a more meaningful comparison with the experimental data can be presented if we deal with these 2 aspects independently. So the temperature scale of each curve and the shapes of the specific heat curves, dealing with them independently. In this chapter, therefore, the experimental values will be compared graphically with the theoretical curves in which the temperature scales are empirical. Chapter 7, the next chapter, will complete the definition of the curves by deriving the relevant temperature magnitudes. So the shapes of the curve will not have like numbers attached to them. The numbers will be attached to them in the next chapter. The temperatures in this first curve will just be relative temperatures. The curves of figure 7 are typical of those of most of the elements. As indicated in figure 4, the final straight line segment of each curve occupies the greater part of the temperature range of the solid state in the case of the high melting point elements. The significant features of the curves are therefore confined to the lower temperatures, and in order to bring them out more clearly, only the lower temperature range up to 300 degrees Kelvin, which is approximately 77 degrees, is shown, Fahrenheit, is shown in the illustrations that follow the remaining sections of the curves. I think it's a little bit more than 77 degrees. Anyway, the curves of figure 7 are extensions of the lines shown in the diagram, except in the case of tungsten, which undergoes a transition to the 4-unit status at about 325 degrees Kelvin. Figure 8 is a similar group of specific heat curves for 4 of the electronegative elements with the negative 0.66 initial level. Aside from this higher initial level, these curves are identical with those of figure 7 when all are reduced to a common temperature scale. The transition to the 2-unit vibration takes place at 4.63, which is 2 1/3 R. Regardless, R is the gas constant. That is the specific heat level. and regardless of the higher initial level. This point will be given further consideration in Chapter 7. The upper portions of the lead and antimony curves, which are not shown on the graph, are extensions of the lines in the diagram. Arsenic and silicon have transitions at temperatures above 300. As noted in Chapter 5, there are a number of elements that undergo a modification of the temperature scale at the first transition point. Two curves with the modified second segment are shown in Figure 9. These two curves actually apply to 4 elements, as the specific heat of lithium follows the aluminum curve, while that of the ruthenium coincides with the molybdenum curve. Coincidence of the specific heat curves of different elements, as in the instances mentioned, is not as uncommon as might be expected. The number of possible curve patterns is quite limited, and as we see in the next chapter, where the nature of the change in the temperature will be explained. The temperature factors are confined to specific heat values, mainly within a relatively narrow range. Also included in Figure 9 is an example of a specific heat curve for an element which undergoes an internal rearrangement that modifies the thermal pattern. The measurements shown for samarium follow the regular pattern up to the vicinity of the first transition point at 35 degrees Kelvin. Some kind of a modification of the molecular structure is evidently initiated at this point in lieu of or in addition to the normal transition to the 2-unit vibrational status. This absorbs a considerable quantity of heat, which manifests itself as an addition to the measured specific heat over the next portion of the temperature range. By about 175 degrees Kelvin, the readjustment is complete, and the specific heat returns to the normal curve. Most of the other rare earth elements undergo similar readjustments at comparable temperatures. Elsewhere, if changes of this kind take place at all, they almost always occur at relatively high temperatures. The reason for this peculiarity of the rare earth group is as yet unknown. Okay, we're going to stop there for today and take over tomorrow here with some more going over some of these specific heat patterns, and then we'll be moving on to the chapter on temperature relations, which is I think just incredible. But anyway, it seems like it's prosaic, I suppose, but get into it and you can figure out that Larson actually has the key to how these things actually operate. And it goes down to the quantum level. So it's exciting. Thanks for tuning in.